Hello. So, in this assignment, we will be talking about the advanced Keras PyTorch, uh, the deep, the other custom deep learning components like learning rate scheduler, dropout, normalization, etc. So, in the first node, first cell, this is just setup and imports being done, and then we are loading the data sets. So the two data sets are loaded here, which is fashion MNIST, which has around 70,000 grayscale images of clothing items across 10 categories. And then we have Housing California, California Housing, which is a data set with information about California and neighborhoods. And it is used to predict the median house prices. Now here is the one cycle scheduler. So the concept is the learning rate controls how big a step the model takes when updating its weight. So if it's too big, it overshoots and never settles, and if it is too small, the training becomes very painful. So that is why adjusting the learning rate is very important. So the one cycle policy solves this cleverly. So it divides the task into phases, 3 phases. So first phase is like the first 43%, 45% of the training. The LR slowly increases from a small value up to a peak. Then comes phase 2, which is 45%. The LR decreases back down. Then comes the final phase, which is phase 3, which is almost the final 10% of the training. The LR anneals nearly to 0. And we implement this as a Keras callback. The plot you see is a smooth triangle wave shape. The learning rate climbs up and then comes back down, then almost disappears. This is called superconvergence because it often lets model learn faster than a fixed learning rate. And how it's built is using Keras callback, a hook that runs automatically at the start of every batch and chases optimizer's learning rate. Then we have my Monte Carlo's alpha dropout, and the concept here is the normal dropout randomly switches off neurons during training to prevent overfitting, like making students study without knowing which questions will be asked. It is turned off during testing. Whereas an alpha dropout is a smarter version of designated cell activation. It preserves the statistical properties like mean and variance of the activations rather than just zeroing values. And Monte Carlo dropout goes one step further. It keeps dropout active even at test time and then run the same input to the model 100 times. So each run gives us slightly different predictions because the random neurons are dropped each time. The spread of the spread of those 100 predictions tell you how confident the model is. If it is very wide, then it means it's uncertain. When it's tight, it means that it's confident. And this is the Bayesian approximations. You're treating the model as is if it fits a distribution of possible models rather than just one fixed model. So the output you see is predicted versus true class labels for 10 samples plus the standard deviation per class for sample 0. And small numbers means high confidence here. Then we have max norm dense layer. So the concept here is max norm regularization puts a hard limit on how large the weights inside the neuron can grow. So after every forward pass, if any neuron's weight has an L2 norm bigger than the max norm, it is rescaled down. So that is the difference from L2 regularizations, which adds a soft penalty to the loss. Max norm is a hard constraint and like a physical clamp. So what's verified here is the code checks that after a forward pass, the max norm uh, mm, max norm of each column should be less than equals to 1. So that is what is printing here. Then we have TensorBoard integration. So the concept of TensorBoard is it's a live dashboard you keep in your browser while training. It shows your training curves, weight distributions, and more, all automatically. And what setup is, we have set up a folder called TB logs with time-stamped subdirectory for this run. The TensorBoard callbacks is attached to the model fit and model.fit. So it writes the metrics like loss and accuracy and the weight histograms after each epoch. And a custom scalar is manually written using the tf.summary scalar. So what you see in the dashboard is a smooth curve of training versus validation. Smooth curve of training versus validation accuracy. Accuracy or loss per epoch, histograms showing how the weights values were distributed, like that. So yeah, that is that. Then we have Huber loss. So most regression models use mean squared errors, which squares the error. This means that one bad outlier gets squared and dominates the loss, pulling the model in the wrong direction. So Huber loss fixes this. For small errors within the threshold, it behaves like MSE, which is mean squared error. But for larger errors, it behaves like an mean absolute error. So it's linear, not explosive. So that is what is implemented here. Now, the two plots you see, the left one is a validation MAE, which is Huber versus MSE. Two lines showing how a validation error drops after 10 epochs. And if Huber, which is the blue one, lowers than MSE, it handles the outline better on this data set. And the right plot is loss shape comparison. This is the intuition chart. The three curves, blue, which is Huber, looks like a parabola in the middle, but flattens to the straight line for a larger error. Red dashed line is MSE, mean square error by 2, which keeps growing as a parabola. So large errors get disproportionately penalized. Then we have green dotted line, which is MAE, which is a perfect line, treats all error equally but it isn't smooth at 0. So yeah, that is the Huber loss. Now we have custom activation, which is custom activation, initialization, regularizer, and constraint. So the 4 components built from scratch. We have leaky ReLU, which is standard ReLU sets a negative value to 0, but if a neuron always outputs 0, it can never learn, which is the dying ReLU problem. So leaky ReLU lets a small fraction of negative signal through. And then we have this my-goal-rolled initializer, which is when the network starts, the weights need to be set to small random values, and bad initialization can cause gradients to vanish or explode. So Glorot, and also known as Xavier initialization, picks value from a range calculated from layer width, keeping the gradients stable at the start. My regularizer is it adds the factor multiplied by sum of absolute weights to the loss. This pushes many weights towards exactly 0, creating a sparse model. useful when you suspect many inputs are irrelevant. Yeah, which is same as L2 regularization, I'd say. And then we have my positive weights, which is after every weight update, clip all weights so none go below 0. So it is useful when negative weights don't make it doesn't make any physical sense. So that is what is implemented here. Then we have custom Huber metric. So earlier we were using the one which is already there in the standard framework, but now we are creating our own, which is so the loss is what the model optimizes. It minimizes during training. So a metric is what you monitor just for reporting. It doesn't affect any training. So the difference in implementation is a metric must handle streaming. It sees data batch by batch and must accumulate a running total. Then the report of a final average at the end of the epoch. So this requires you to state variables, two state variables total and count at each epoch. So the plot you see, two lines, the training Huber loss, which is the solid blue, and the validation Huber loss, which is the dashed blue. So decreasing over 8 epochs, and ideally both decrease together. If validation stops improving but training keeps going down, the model is overfitting. Then we have custom layers. So we have made we have 4 layers built from scratch. So the first is exponential layer, which applies e to the power x to every neuron output. It is useful when output must be positive, like rates or counts. And then we have myDense. Then we have myDense, a complete dense model, dense layer, hand built using the add weight for the kernel and the bias multiplication for forward pass. This is exactly what layers.dense does internally. Seeing it written out demystifies the magic, I would say. Then we have the add Gaussian noise. It is during training, add small random noise to the inputs. So this acts like a data augmentation, and it prevents the model from memorizing the exact training examples. So at test time, the noise is switched off, and then you just see the clean predictions. This is just done at the time of training. Then we have my layer normalization. It normalizes each sample across its feature independently and not across the batch. And this is important for models where batch statistics are unreliable. Small batches are in an unlearnable gamma scale. Then we have the residual regressor. So the concept is in very deep networks, gradients get weaker and weaker as they travel backward through many layers. So vanishing gradient problem. And skip connections, which is also called as residual connections, solve this problem by adding the input to a block directly to its output, which is f of output equals to f of x plus x. So this gives gradients a shortcut to flow through. So the residual block, which has 2 layers with the ELU activation plus the input added at the end. The block learns only the difference from the identity, hence residual learning. Then we have a residual regressor, which stacks 4 of these blocks with an initial projection layer to get the right width and a single output neuron at the end of the price prediction. The plot over here is the training MAE, which is the blue line, and the validation, which is the red line, dropping over 10 epochs, and both should trend downward together. Then we have momentum optimizer, which is the plain CDG, stochastic gradient. It updates weights by stepping in the direction of the gradient. With momentum, you maintain running velocity. So the direction you have been consistently going, this smooths out noisy gradient updates and accelerates movement in consistent direction like a rolling ball. So yeah, the updated rule over here is velocity equals to point, 0.9 into overall velocity plus gradient, and the weights are weights minus learning rate into velocity. So what we have built over here is a full Keras optimizer subclass with built function to initialize one velocity variable per weight tensor and update step to apply momentum update each step. Now we have the PyTorch custom training loop. So in Keras, you just call model.fit and everything happens automatically. So in PyTorch, you write the training loop yourself, which gives you the complete control. So in the 5-step loop per batch has optimizer.zero guard clear, which clears all the gradients from the previous batch. Prints equals to model with the input, which is the forward pass. Then we have compute loss. Then we compute gradients. Then we compute gradients. Then we update the weights. Then we are now the model versus train. So training mode enables dropout, and eval mode disables dropout. So predictions are deterministic, and forgetting to switch mode is a common beginner bug. And no grad is during evaluation you don't need to compute gradients, and it saves memory and time. And step-LR is the scheduler and halves the learning rate every 3 epochs, which lets the model make finer adjustments as it gets closer to the optimum. Then we have the 2 plots, which is the left one is loss over 8 epochs. Both train and validation should decrease if the validation loss rising while training loss keeps falling. That means the model is overfitting, which is not the case over here. Same here, right side we have the accuracy. Both lines should climb. You would typically expect 87 or 89% accuracy on the fashion MNIST with this architecture. Then we have weights and bias. So when you run many experiments, keeping track of many experiments like we did so in this notebook, different learning rates, model size, etc., keeping track of results in your head or spreadsheet quickly becomes unmanageable. So weights and bias is a cloud platform that automatically records every run for you, and what gets logged is all the hyperparameters like learning rate, batch size, etc. as a config, and the train and validation accuracy and loss per epoch via weights and bias metric logger. Then we have a custom table, and let me see if it is still open or not, the dashboard. Yeah, it is there. Here you can see the filter based on each class, the accuracy of the classes, the epoch, validation loss, validation accuracy, and the other things you can see over here. So yeah, basically it provides you a dashboard with overlay training curves for every run, and a table comparing final metrics, and a chart highlighting which hyperparameters matter the most. Yeah, so that is GPU usage also you can see. Yeah, that is pretty much it in this notebook. Yeah, thank you.